Hi, so today's lesson is going to be about measurement. Measurement is basically a quantitative type of observation. So when you take a measurement, you get data, and data is important not only in chemistry but also in other fields like biology, physics, and engineering. Every measurement contains two things: a number and a unit, like grams, kilograms, meters, miles, yards, and so on. And so when you take the mass of an object, you always want to make sure that you take note of the unit. Let's say the mass of the object was 50 grams. In your lab book, you need to write 50 grams and not just the number 50. In every measurement, accuracy is important. It is cost efficient. Inaccurate measurements, on the other hand, are wasteful, both in terms of resources and time. And so, in order to reduce this inaccuracy, a lab experiment is typically performed a minimum of 3 trials, which means you would make multiple separate measurements, and then statistical analysis is used to show how accurate and reliable your measurements are. You look at things like the average and standard deviation. Measurements can involve both large and small numbers. Large numbers can be in millions and billions, whereas small numbers can be in small fractions or even in micro level and nano level. Like, for example, large numbers such as 1 million or 532,156,781,000 miles, or smaller numbers like 0.00154 second or 0.000032 milliliter. So in chemistry, we deal with a lot of large numbers, extremely large numbers, and sometimes extremely small numbers. And we don't want to keep writing a bunch of zeros. And so we have to find a way to simplify these large numbers or small numbers. And so we use scientific notation. And scientific notation is basically used to show numbers, large and small, in a more concise format. You can think of it like a shortcut, a simplified version of a large number or a small number. Scientific notation involves two things. One is coefficient and the other one is a multiplier. And so when you see a standard notation written in scientific notation, it would look something like this. So for example, 3 million can be written in scientific notation shown here. So this right here is 3.0 times 10 to the 6th power. Okay, so you have the coefficient, which is 3.0, and the multiplier, which is 10 to the 6th power. So you have the number 10 raised to a power. And that's what they call a multiplier. So you can have multipliers like 10 to the 1st power, 10 to the 2nd power, 10 to the 3rd, all the way to 10 to the x power, where x can be any number. So let's look at more examples and see how multipliers actually work. So here's a bunch of numbers, right, from 10 to 100 million. And we don't want to keep writing a bunch of zeros. And so we have to use exponents, right? So the number 10, you can rewrite this in the form of a multiplier, or a power of 10, by simply using the number 10 and then raise it to some number, right? And so the superscript, the number 1 up top, it basically represents the number of zeros. And so we know that the number 10 has 1 0. And so when you convert this into a multiplier, it's basically the number 10 raised to the 1st power. And then looking at the next one here, we have 100. And so the number 100 contains 2 zeros. And so the multiplier would be 10 to the 2nd power. 1000 has 3 zeros, so this would be 10 to the 3rd power. 10,000 has 4 zeros, so this is 10 raised to the 4th power, and so on and so forth. So 100 million would be 10 raised to the 8th power, because you have a total of 8 zeros. All right, so these are multipliers or positive. So these multipliers contain positive exponents. But what about multipliers containing negative exponents? And what do these negative exponents tell us? So let's look at some numbers a lot less than 1, right? So these are basically fractions. So you have 0.1, 0.01, 0.001, all the way to, let's say, 0.000001, right? So a bunch of zeros. So we don't want to keep writing these zeros again, and so we have to find a way to simplify it, and we can use multipliers. So let's look at this in a simple way. When you look at the number 0.1, 0.1 is basically equivalent to 1 divided by 10. So when you plug in 1 divided by 10 in your calculator, you get 0.1. Okay, so in that case, the next one here, 0.01, is the same thing as 1 over 100, or 1 divided by 100, and you get 0.01. And then the third number is 1 over 1,000, and then 1 over 10,000, all the way to 1 over 100 million. Right? And so again, we still don't want to keep writing a bunch of zeros in fraction form, but you can kind of see these denominators here are factors of 10, right? And so let's look at the second number here, 0.01, which is equivalent to 1 over 100. We can simplify that into 1 over 10 raised to the second power, because 100 has 2 zeros. And then now you can look at the first number here, 1 over 10. That's basically equivalent to 1 over 10 raised to the first power, because 10 has 1 zero. And then for the third number here, we have 1 over 1,000, which is equivalent to 1 over 10 raised to the third power, because 1,000 has 3 zeros. And then last one, or the fourth one here, is 1 over 10,000, so that's equivalent to 1 over 10 raised to the fourth power. And then you can kind of see the sequence here for the rest of the examples here. All right, so when you have a fraction, right, raised to some exponent, 1 over 10 to the first power, you can simplify this further so it's not in fraction form. So when you have 1 over 10 to the first power, you can replace this and turn it into a negative exponent. So this -1 tells you that you have a fraction, 1 over 10. Okay, so a negative exponent basically represents a number less than 1. Okay, and you can do the same thing for the other numbers here. So 1 over 10 raised to the second power is equivalent to 10 to the -2. And the next one is 10 raised to the -3. And then the fourth one is 10 raised to the -4, and so on and so forth. So these are all examples of multipliers with negative exponents. So again, if you have a positive exponent, that tells you that the number is greater than 1. And a negative exponent indicates that the number is less than 1, as in 0.1, 0.01, basically any numbers less than 1. Okay, so let's look at some examples here and show how to convert a regular number or a standard notation into scientific notation. So again, a scientific notation contains two things. The first one is a coefficient, and a coefficient contains a single digit followed by a decimal point and then another digit, and also a multiplier, okay, which is the number 10 raised to an exponent. And we have examples here up top, 3.4 times 10 to the 8th power, 8.45 times 10 to the -3, and 6.02 times 10 raised to the 23rd power. So let's look at the examples here on the left, which says convert to scientific notation. So looking at the first number here, 12,000, right? We know that 12,000 is greater than 1, and so you would expect this number to have a positive exponent when you convert it to scientific notation. And so looking at the coefficient, what would be the coefficient of this number? Well, we know that a coefficient contains a single digit followed by a decimal point and then another digit. So in this case, it would be 1.2. So that's going to be our coefficient, and then multiplied by a multiplier, right? And so you look at how many places or how many spaces you move that decimal point to get to 1.2. So you can see that we moved the decimal point 4 places to the left, right? So because we moved it 4 places, our exponent is going to be 4. Okay, so it matches the number of times you move that decimal point. And because the number is greater than 1, then we know that the exponent is going to be positive. So you probably learned this back in high school or middle school, where they tell you if you move the decimal point to the left, then it's going to be a positive exponent, and if you move it to the right, then it's going to be a negative exponent. That's a little bit confusing, and so I want you to slightly change your mindset and think of the number instead. If it's greater than 1, then it's going to have a positive exponent, regardless of what that number is. And if the number is less than 1, whatever that number is, it's always going to have a negative exponent. So now we have 0.00012, right? So you know that this number is less than 1. And so you know that the exponent is going to be negative. And so in order to turn this into scientific notation, we got to look at the coefficient. Again, our coefficient is going to have a single digit followed by a decimal point and then another digit. So in this case, we have 1.2. And then you include the multiplier, which is 10 raised to an exponent. So now you're going to look at how many places you move that decimal point to get to 1.2. In this case, it's also 4 places to the right. And so because we moved it 4 places to the right, it's going to have an exponent of 4, but also negative. So it's negative 4. So 10 raised to the negative 4th power. All right, so now let's look at the example here on the right. Convert these scientific notations into standard notation. So the first number here is 8.32 times 10 raised to the negative 5th power. So you can see that this is a negative exponent, so you know that this number is going to be less than 1, a fraction. And so what we're going to do is we're going to move that decimal point 5 places to the left because you're turning it into a number less than 1. Because if you were to move that decimal point 5 places to the right, then that's going to be a positive, it's going to be a number greater than 1, and so it has to be moving to the left. All right, so in that case, we have 0.0000832 because we moved that decimal point 5 places to the left. And the last one here is 1.45 times 10 raised to the 6th power. And so because we have a positive exponent, you're going to move that decimal point 6 places to the right. So we have 1,450,000. Let's look at a few more examples here and convert standard notation to scientific notation. Again, you can pause this video if you want to give them a shot. So the first one here on the left is 11,000. How would you convert this to scientific notation? So again, a scientific notation requires a coefficient. Our coefficient in this case would be 1.1. And then look at the multiplier. So we move that decimal place, decimal point 4 places, okay, to get to 1.1. And so in this case, it's 1.1 times 10 raised to the fourth power. The exponent is positive because 11,000 is greater than 1. The next two examples here, 5 million and 32,400, are both numbers greater than 1, and so you would expect them to have positive exponents. So 5 million, our coefficient is going to be 5.0, and then the multiplier would be times 10 raised to a positive exponent. So in order to get to 5.0, you would need to move that decimal point 6 places to the left. And so the scientific notation for 5 million is 5.0 times 10 raised to the 6th power. The third one here is 32,400, so that would be 3.24 raised to the 4th power. Next one here, the next three numbers are numbers less than 1, and so you would expect them to have an exponent, a negative exponent. So 0.0001, the coefficient would be 1.0, and in order to move that decimal point to 1.0, you would have to move it 4 places to the right. So it would be 1.0 times 10 to the negative 4th power. 0.0351 would be 3.51 times 10 raised to the negative 2nd power. Okay, what about 0.0000054? So our coefficient is going to be 5.4, and then we're going to move that decimal point 7 places to the right, and so it would have a negative 7 exponent. So 5.4 times 10 to the negative 7th power. Next one here, the next two are greater than 1, and so they will have a positive exponent. We have 324 billion, which in scientific notation would be 3.24 times 10 raised to the 11th power. All right, and the next one here is 767,453,251,000. So in order to convert this to scientific notation, your coefficient is going to be 7.67453251. The reason why is because you have to include all the non-zero digits in your coefficient. And the reason why has something to do with significant digits. And we'll talk about significant digits later on in this lesson. So that would be 7.67453251 times 10 raised to the 11th power. All right, and the last two examples here are numbers less than 1. So you would expect them to have negative exponents. So the next one here is 4.56 times 10 to the negative 4th power. And the last one is 3.205 times 10 raised to the negative 3rd power. All right, and here's a few more examples. This time you're converting from scientific notation to standard notation, which is basically a regular number. So the three examples here on the left all have positive exponents, and so they will be greater than 1. These numbers are all greater than 1. So the first one here is 1.01. Multiply this by 10 to the 5th power, so that would be 101 and then 3 zeros, right? So that would be 101,000. Second one here is 3.34 times 10 to the 3rd power. So in standard notation, This is 3,340. You're basically moving that decimal point 3 places to the right because this is a positive number. Or I'm sorry, this is a number greater than 1 because of the positive exponent. All right, and the third example here is 4.0 times 10 raised to the 6th power. Again, 10 to the 6th power is essentially 1 million. And so you have 4 million. Or you can move that decimal point 6 places to the right, which you will get 4 million. All right, all the numbers on the right-hand side, we have 10 raised to the negative 3, negative 9, and negative 6. So these are all numbers less than 1. So you're going to have to move that decimal point to the left. So with 1.85 times 10 to the negative 3 power, you move that decimal point 3 places to the left. So we have 0.00185. The next number here is 2.3 times 10 raised to the negative 9 power. So you're going to move that decimal point 9 places to the left. So that would be 7 zeros. Okay, so it'd be 0 decimal point and then 7 zeros, 2, 3. Okay, my mistake. That's actually 8 zeros and then 2, 3. And then finally, we have 4.01 times 10 raised to the negative 6 power. And so you would move that decimal point 6 places to the left. So that would be 0 point followed by 5 zeros and then 401. So it's 0.00000401. Every measurement has a unit. So units like grams, kilograms, miles, yards, seconds, so on and so forth. And so it's important that we talk about the different units of measurement. These are basically quantities with accepted values that can be communicated between people. There are 2 types. There's the English system, also known as the imperial system, and there's also the metric system. And so here in the US, we use the English system, and everyone else uses the metric system. So miles, yards, feet, gallons, quarts, pounds, ton, these are all examples of units in the English system. Whereas in the metric system, you have the meters, liters, grams, and some others. The first 3 here in the English system, like miles, yards, and feet, and the meters, these are all units for distance or length, right? The next couple ones here, gallons, quarts, and liters, these are all units for volume. And the last one, pounds, ton, and grams, are all units for mass. But our main focus here is going to be on the metric system because this is relatively easier to use compared to the English system. And this is also the system that's used predominantly in the STEM field: science, technology, engineering, and mathematics. And these are the most commonly used units in chemistry. We have the meter, liter, grams, Celsius, and Kelvin, which is the absolute temperature. And so make sure you know these units and also the symbols for these units. So again, for meter, we have little m, liter, capital L, gram, little g, Celsius, capital C, Kelvin, capital K. So before the metric system, we had a lot of different units. And converting from one unit to another made it a little bit confusing and complicated, especially in international trading. And so the French people, later on in the 1700s, they came up with a standardized unit of measurement. And so they called it fundamental SI units of measurement. So SI in In French, it's Système International. I don't really know how you would pronounce that in French, but in English, it's international system. Okay, so international system, units of measurement. For mass, the SI unit of measurement is the kilogram, which has a symbol kg. For length, the SI unit is meter. For time, it's seconds. For temperature, it's the absolute temperature, which is Kelvin. And for the amount of substance, it's the mole, with the symbol MOL. Okay, and so you'll learn a lot more about moles later on in this course. So what makes the metric system a lot simpler to use compared to the imperial system is because of the fact that it uses prefixes to make conversions between units a lot easier from a large number to a smaller number and vice versa. And the main reason is because it uses factors of 10, 100, 1,000, so on and so forth. They're all divisible by 10. So what are these prefixes? There's a lot of different prefixes in the metric system, but they're easy to remember. The first one is kilo, and you've heard of this: kilograms, kilometers, and so on and so forth. And it has the symbol lowercase k. There's also mega, which is larger than the kilo, like megabytes, right? And mega has the symbol capital M. There's gigabytes, capital G, and tera, capital T. There are also the smaller units, like centi. So centi has the symbol C, milli, lowercase m, micro has the symbol that looks like a sexy U, nano, lowercase n, and pico, lowercase p. All right, and there are other prefixes that are less commonly known and used, like deci, right, lowercase d. There's the hecta, lowercase h, and deca, lowercase da. And the letter capital U here is basically a filler. It's the main units, like the grams, liters, seconds, and meter. And all these prefixes, so these are all the symbols, they also have numerical values. Okay? They have a numerical value. Like, for example, the kilo is worth 1,000. Okay, so 10 to the third power is basically equivalent to 1,000, because the number 1,000 has 3 zeros. And so when you convert that into a multiplier, you get 10 to the third power. So these are basically multipliers here, the numerical values. So kilo is 10 to the third, hecta is 10 to the second power, deca is 10 to the first, and then once you get to the main unit, you give it 10 to the 0 power, which is also equivalent to 1. So when you plug in 10 raised to the 0 power, that's equal to 1. So you're basically just counting down here: 10 to the third, 10 to the second, to the first, 10 to the 0, and then 10 to the negative 1 for deci, 10 to the negative 2 for centi, and 10 to the negative 3 for milli. So I'm going to box this in, these units and the numerical values. And the reason why is because once you move outside the box, the factors change, or the numbers change by a factor of 1,000, these numerical values. So for example, looking at micro, right? From 10 to the negative 3, and then it jumps to 10 to the negative 6. So instead of like from deci all the way to milli, it's 10 to the negative 1, then negative 2, negative 3, and then it jumps outside the box, right, to 10 to the negative 6. And same thing with nano. Now it jumps by a factor of 1,000, so 10 to the negative 6, 10 to the negative 9, and then 10 to the negative 12. And you can see the same trend to the left side of this box. So from kilo to mega, that's a jump of a factor of 1,000. So from 10 to the third power to 10 to the sixth power. And then from 10 to the 6, you get giga is the next one, 10 to the ninth, and then from giga to tera, 10 to the 12th power. So these are all the numerical values of each of these prefixes. So the importance of this is the fact that you can convert from one small unit to a large unit and vice versa, from large to small, right? So let's say I have 1 meter, right? 1 meter or 1 liter. Let's go with meter, 1 meter. And if you put a K there in front of the meter, let's say 1 km, that 1 km or 1 kilometer is equivalent to 1 times 10 to the third power meter. In other words, 1,000 meters. Because that prefix K is equivalent to 1,000. And so if you put 1 km, you just replace that K with times 10 to the third power, and you get 1,000 meters. Okay, and we'll talk more about the metric system and converting from one unit to another later on in this chapter. And again, these are the main units. You have the grams, the liters, meters, and seconds. And here are some examples of different units and also their symbols. So the first one is milliliters. So milli is little m and liter is capital L. So milliliters would have the symbol lowercase m, capital L. So ml. Centimeters would be lowercase c and m. Nanoseconds would be lowercase ns. Kilograms would be kg. Megabytes would be capital M, lowercase b. Micrograms would be the symbol for micro, which is sexy letter U, and then G for grams. Picoseconds would be lowercase p and lowercase s. And gigagrams would be capital G, lowercase g. So GG. So again, accuracy is very important in every measurement. But there's actually a difference between accuracy and precision. So by definition, accuracy refers to the reliability of a measurement. And this is usually compared with a known true value. Precision, on the other hand, refers to how close your individual measurements are relatively to one another. So I'm going to demonstrate the difference here by looking at a target, right? A bullseye right here. And so let's say that you have three shots, okay? And you hit the bullseye. This is considered accurate measurement or accurate shots, and also precise. The reason why it's accurate is because if you treat the bullseye as the true value, then you've reached that true value. So it's pretty accurate. It's precise because the spacing between the hits are very small, right? They're very close to each other, and so that's what we consider a precise shot or measurement. So this is both considered accurate and precise. Now, the second illustration here shows you accurate measurement or accurate shots because it's still the three shots still hit the bullseye. But the difference here now is that these hits are far away from each other. And so this is considered imprecise. It's accurate, but not precise. Here's another example. Now you have these 3 hits that are very close to each other, but outside the bullseye. And so this would be considered inaccurate, but precise. And the last example here, you have all the 3 hits far away from each other and not hitting the target. And so in that case, this is considered both inaccurate and imprecise. So make sure you know the difference between these two terminologies. So now this brings us to this concept known as significant digits. And so significant digits basically tells us how reliable and accurate a measurement is just by looking at the number of significant digits. Significant digits is also known as significant figures, or simply sig figs. And as I've mentioned earlier, this tells us how reliable and accurate a measurement is. The more the number of sig figs you have, the more reliable and accurate the measurement is. And these are basically the digits contained in a measured value. So for example, if you were to measure the volume of some substance, some liquid, and one measurement tells you it's 48.1 milliliter, and the other measurement tells you it's 48 milliliter, which one do you think is more accurate? Well, you have to count the number of significant digits. And so the first one here would be considered more accurate because it contains 3 significant digits or significant figures, whereas the second one only contains 2. But I guess the question is, how do we count the number of significant figures? So in order to count the number of significant figures or significant digits, there are rules and steps that you need to follow. And this is actually the concept that a lot of the students have a hard time grasping. And I think the main reason is they overthink it. And so I'm going to walk you through this step by step, rule by rule, and you should be fine. So the first rule here is that all non-zero digits are considered significant. Okay, so non-zero digits like 1, 2, 3, 4, 5, 6, 7, 8, 9, right? These are digits that are non-zero, and so you would count them as significant. So let's look at some examples here. Let's say the first one, 135 centimeters. So you made a measurement and you wrote it down, it's 135 centimeters. How many significant digits are there in this measurement? Well, they're all non-zero digits. And so every single digit in this measurement is considered significant. And so 135 centimeters contains 3 significant digits or sig figs. All right. For the next one here, let's say you're timing an experiment and you got 75 seconds. Okay. So you wrote down 75 seconds. Both digits are non-zero digits, and so you would have 2 significant digits for this measurement. And then the last one, 3,896 milliliters, you have 4 digits here, and they're all non-zeros, and so they all count as significant digits. So you have a total of 4 sig figs. Okay, so the first rule is pretty simple, right? You don't have to overthink it. All non-zero digits are considered significant. The second rule here states that zeros in between 2 non-zero digits are considered significant. So we can call this zeros in between, right? The zeros in between. So like for example, if you made a measurement and you got 503 centimeters, there's a 0 in between 2 non-zero digits that are significant. So we have a total of 3 significant digits. So that 0 that's in between 5 and 3 is considered significant. So you count it. So for the measurement 503 centimeters, you have a total of 3 significant digits. Now the second one's a little bit tricky because now you have 2 zeros that are in between 2 non-zero digits. So does that mean that we count both of them? And the answer is yes. These 2 zeros are in between 2 non-zero digits. And so both zeros do count as significant. So in this measurement, 2,004 milliliters, you have a total of 4 significant digits. And the last one is 40,609 seconds. So again, you have 2 zeros, right? 1 0. The first 0 is between 4 and 6. And then the second 0 is between 6 and 9, which are all non-zero digits. So again, these 2 zeros are considered significant. And so you would count them. So how many total significant digits do we have for this one? 5. All right. And the third rule is states that leading zeros are not significant. Leading zeros are never significant. So these are zeros that are up front, right? Typically in numbers involving decimal points. So let's look at some examples. 0.00321 centimeter. So you made a measurement and you got 0.00321. You can see that the first three zeros are considered leading zeros, and you don't count them. They're not considered significant. So for this measurement, you have a total of 3 significant figures. The next one here is 0.00567 liter. And so again, you have 2 leading zeros, and they don't count. And so you only have 3 sig figs for this measurement. And the last one, we have 0.000105 second. Again, the first 4 zeros are leading zeros and they don't count. And so you have a 0 in between 2 non-zeros, 1 and 5. And so that 0 in between 1 and 5 will be considered significant. And so you would count it. So you have a total of 3 sig figs for this measurement. So now the fourth rule involves trailing zeros. And these are the zeros at the end of a number. And there are 2 different types of trailing zeros. The first type is a number that does not contain a decimal. Okay? So if you have trailing zeros in a number that does not contain a decimal point, then those trailing zeros are considered not significant. Okay, here are some examples. So if we have 10,000 grams, so you have those 4 zeros, those are all trailing zeros, and you don't see any decimal points here. And so 10,000 would only have 1 significant digit, or 1 sig fig. The next one here is 530. That 0 doesn't count because, again, this is a trailing 0, and you don't see any decimal point. And so you only have 2 significant digits. And the last one here is 840,200 seconds. You have 2 trailing zeros and 1 0 in between 4 and 2. And so that 0 in between counts as significant digit. But the last 2 trailing zeros are insignificant. And so you don't count those. So for this example, you have a total of 4 sig figs. And the second rule involving trailing zeros is the one that contains a decimal. So if you have a trailing 0 that contains a decimal, they count as significant digit. Okay, let's look at some examples here. So, for example, 100.0 liter. Okay, you have 3 trailing zeros. Okay, you have 3 trailing zeros, and there's a decimal point somewhere right there. So all these trailing zeros will be considered significant. So for the measurement 100.0 liter, you have a total of 4 significant digits. Second one here, 121.00 gram. You have 2 trailing zeros, and there's a decimal point. Those zeros count. So you have a total of 5 significant figures. And the last one here is 506.000. And you have 3 trailing zeros, 1 in between 0, a total of 6 significant figures. So the last rule here involving counting significant figures or significant digits involve numbers that are exact, right? So exact numbers basically have unlimited number of significant figures. So for example, if I counted that there are 30 students in this class, then that has an unlimited number of significant digits. So 30, if you just, let's say 30 meter is a measurement, you would think that you would consider that as 1 significant digit because the 0 is a trailing 0 and it's considered insignificant. But in a counted number, like 30 students, 30 has unlimited number of significant digits. Same thing with 10 dozen roses, because that's a counted number. Conversion equivalents like 1,000 milligram per gram, or 1 gram per 1,000 milligram, or let's say 14.0 psi per 1 atmosphere. These are all equivalents, right? And so they have unlimited number of sig figs. Numbers that are part of an equation, like for example, area equals pi r squared. You have pi, right, which is equivalent to 3.1416, so on and so forth. That's considered unlimited number of sig figs. Same thing with 1/2 in the formula for kinetic energy, right? Ke kinetic energy equals 1/2 mv squared. That 1/2 there is considered an exact number, and it has unlimited number of sig figs. Same thing with equation for volume. Volume equals 4/3 pi r cube. So the 4/3 pi has an unlimited number of sig figs. Absolute temperature, like the Kelvin, for example, if we have 500 kelvins, 300 kelvins, they also have unlimited number of sig figs. And so what this really means is that they don't affect the counting of sig figs, and whenever you're calculating specific measurements and stuff like that, so they won't have an effect in the number of sig figs overall. And I'll talk about this in a little bit more detail once we get there, which is in a couple of slides. Significant digits, if you remember, tells you the reliability and accuracy of a measurement. And so when you make a measurement, you have a certain number of significant figures for that specific measurement. And then if you apply that to a formula, you don't want to lose that accuracy or reliability. You don't want to lose that number of significant digits. And so how do we deal with counting number of significant digits in mathematical calculations or operations? So there are some rules, and the first one involves multiplication and division. And I think this is easier compared to subtraction and addition. So let's focus on multiplication and division and how we can keep the number of sig figs for these operations. So in multiplication and division, the calculated number, the resulting number, has the same number of sig figs as the number with the least number of significant figures. Okay, so let's look at some examples. Let's say 10.00 times 1. We know that the answer is 10, but you have to report this with the proper number of significant digits. So we're going to compare the two numbers, right? The first number here, 10.00, has 4 significant figures. You have 3 trailing zeros, and there's a decimal point. So a total of 4 sig figs. The second number, 1, only has 1 sig fig. And so your calculated number should have the same number of sig figs as the one with the least number of significant digits. So in this case, the answer should only contain 1 significant digit. In that case, 10. So 10 contains 1 sig fig, which is the same as the number with the least number of sig figs. So you would report your calculated answer as 10. Here's another example. 10.00 times 1.00. Okay. Again, the first number here has 4 sig figs, and the second number has 3 sig figs. So your final answer, or the calculated answer, should contain 3 significant digits. So in this case, 10.0, right? So you would add a decimal point followed by another 0, because you're turning it into a trailing 0 with a decimal point. So now you have a total of 3 significant figures. And the last example here is 10.00 times 1.0. First number has 4 sig figs, second number has 2, and the answer is 10, right? But then the number 10 only has one significant figure because that 0 is a trailing 0. So how can we turn this into something that contains 2 significant digits? Well, you can add a decimal point right after the 0, and that would give it 2 significant digits. Or you can turn this into scientific notation, 1.0 times 10 raised to the first power. So whenever you're counting number of sig figs in scientific notations, and this is important, you only look at the coefficients, right? So when you look at the coefficient, the coefficient is 1.0. And so 1.0 has 2 significant digits. So you can report it either way, 10 point or 1.0 times 10 to the first power. Although it is preferable to use scientific notation. All right, in division, same idea, it's the same concept. You're going to compare the two numbers and see which one has the less number of sig figs. So 100.0 divided by 10.0, 4 sig figs compared to 3, so you go with the less number of sig figs, so the answer would be 10.0. Next one here, 100.0 divided by 10, you have 4 sig figs up top compared to 1 in the denominator, and so the final answer would only have 1 significant digit, which is 10. Another example here, we have 100.0 divided by 10.00. So they both have 4 significant digits, and so the final answer should also contain 4 significant digits. All right, and the last example here is 15,730 divided by 121. Plug it into the calculator and you get 130, right? And so you have, let's say, a total of 4 significant digits on the number up top and 3 sig figs at the bottom. And so the final answer should also contain 3 significant digits. And with 130, the only way you can get 3 significant digits is if you add a decimal point right after the 0, or you can turn this into scientific notation. And so now you have 3 significant figures. All right, so before we get into addition and subtraction, I want to go over how to round up or down to a specific number of significant figures. The reason why is because whenever you're performing a mathematical calculation or operation, sometimes you get a lot of numbers in the calculator, right? The calculator spits out, let's say, 4.505678 whatever. But whenever you're reporting your calculation properly, sometimes you have to round up or round down to the correct number of significant digits. So let's look at how to do that. When rounding a number to, let's say, 2 significant figures, underline the first 2 significant figures going from left to right. If the next digit is greater or equal to 5, then round the second digit up, otherwise round down. Okay? So let's look at some examples here. Round the following to 2 significant figures. Here are the numbers. So the first one is 4.168. How do you round this to 2 significant digits? So according to this step here, you look at the first 2 numbers from left to right. You underline them, and then you look at the third number and see if that's greater than 5 or equal to 5, which then results in the rounding up of the second number. So the third number here is 6, which is greater than 5, and so you would round up the second digit. So you rounded it to 4.2. The second number here is 5.482. So you underline the first two numbers, and then you look at the third number, which is also greater than 5, and so you would round up the second digit, and you would report it as 5.5. And the third number here, again, you can always pause this video if you want to try the rest on your own. So number 3 here is 4.148. You underline the first two, and look at the third number. If it's greater than 5, you round up, otherwise you round down. So because we have 4, it's less than 5, you would round everything down, and so you would report this as 4.1. So that's a typo. Okay, so 4.1. The fourth number here is 5.446. Again, you're going to underline the first two numbers, and the third number is 4, which is less than 5, so you round down to 5.4. The fifth one is 8.710. The third number is 1, which is less than 5, so you round it down to 8.7. And the last one, we have 0.00345. Underline the first two significant figures, and the zeros are trailing zeros, so you skip those, and you underline 3 and 4. And then you look at the third number, which is equal to 5. And so we round this up to 0.0035. And here's a few more examples. Round the following to one significant figure. First number here is 110, right? So because we're rounding this to only one significant figure, you would underline the first sig fig that you see from left to right. And so 1, the first one is significant digit, and then you're going to look at the second digit and see if that's greater than 5 or equivalent to 5, which is less than 5. And so we're going to round it down to 100. Next one is 24,000. You underline the first digit that you see, and because the second digit is less than 5, you would round this number down to 20,000. Third one is 539,000. We have the first significant digit as 5, and then compare 3 with 5. We round it down to 500,000. Number 4, 150. We would round it up to 200. 360, we have the second digit is 6, so we round this up to 400. And the last one, 0.00160, again the first digit, the first significant digit from left to right is the number 1, so you would underline that, and since 6 is greater than 5, you would round this up to 0.00200. Oh, 0.002, because we're only rounding it to one sig fig. So it's not 0.00200, because if you added the 2 zeros there, those would be considered trailing zeros containing a decimal point, and they would count as significant digits. So you would stop at 2.002. So now this brings us to addition and subtraction, which is a little bit more complicated compared to multiplication and division when it comes to significant figures and rules of counting. So let's look at some examples here. Let's say we look at the first one, 3.62 plus 0.255. What would that be equal to? So the first thing that you want to do here is to rearrange this mathematical operation to look like this. So you're going to realign the numbers and the decimal points, and then you would perform the calculation normally. So 3.62 plus 0.255 gives us 3.875. But how do we report this to the proper number of sig figs, right? So the rule is a little bit different. And so the first thing that you want to do here is to look at the first number, 3.62. And so you're going to draw a line from right to left until you hit that very first significant digit, which in this case is 2. And so you're going to underline that first digit that you encounter and then move on to the next number. So the next number here is 0.255. So we're also going to draw an arrow or a line until you hit that first significant digit, which is 5. So we're going to underline that. And then we're going to compare these two underlined numbers. The number that's farther to the left, you would draw a line behind it, a vertical line, right? So number 2 is the number that's farther to the left, and you're going to draw a vertical line behind it. And so now, all the digits on the left-hand side of this vertical line are considered significant. And all the numbers that are on the right-hand side of the vertical line are considered insignificant. And so you don't count them. And so how do we report this answer? Well, you can underline the significant digits, 3, 8, and 7, but then you would have to round this up, right? Because the number after 7 is 5. And so anything that's 5 or greater, you would have to round up the preceding number. So in this case, you would report this to 3 significant digits, and it's 3.88. And you can do the same thing for the second and third examples here. So for the second example, again, you're going to have to realign these numbers and decimal points. And you would perform the subtraction or the addition normally, and we get 21.455. And then you follow the procedure. You're going to draw a line from right to left until you hit the very first significant digit. So for the first number, that would be 5. For the second number, that would be 2. And then you're going to compare the two numbers and see which one is farther to the left. Whichever it is, you draw a vertical line behind it. And then now you underline, so the numbers that are on the left-hand side of the vertical line are considered significant. And then again, you would report this to 3 sig figs, rounding up the 4 to 5. So that would be 21.5. And here's the last example, 10,000 plus 1,000. This gives us 11,000. And then you would follow the same step-by-step procedure here. You're going to draw a line or an arrow until you hit that very first significant digit. In this case, that would be 1 for the first example. And then, first number. And then the second number, you would do the same thing. Draw an arrow or a line until you reach that first significant digit, which is also 1 in this case. And so you're going to compare those two underlined numbers. The farther to the left, you would draw a vertical line behind it. And the digit that's to the left of that vertical line is considered significant. And so you would report this to only 1 sig fig. And the answer would be 10,000. You would have to round this down because the next digit is 1. All right. So now how do we apply this concept of significant figures or significant digits in measurements, right? Because again, the higher the number of significant digits, the more reliable and accurate the measurement is. So how do we know that a measurement is accurate or relatively more accurate compared to another measurement? So first, let's look at mass whenever you're taking the mass of an object, right? So when using a digital balance, report all the numbers shown as significant figures. So for example, if you were to weigh an object and the digital balance reads 34.930 grams, then you would have to report all the numbers as significant. So you would have a total of 5 significant digits for that specific mass measurement. So that's simple for mass. Now let's look at volume. Okay, let's say we have 2 different graduated cylinders here. So this is a graduated cylinder and it's used to measure volume of liquids. and these two are different in terms of the markings, right? So the one on the left only has specific marks like 1, 2, and 3, and the graduated cylinder on the right has subdivisions, right? Little marks. So you have major marks and minor marks here. All right, so how would you read liquid measurements, right? The volume of a liquid. So whenever you're looking at the volume of a liquid, you have to look at it at eye level. Okay, so you would have to look at what they call the meniscus, and this meniscus is basically the bottom of the curve, the very bottom of the curve, and you have to look at it at eye level. And so whenever you look at this, or whenever you're taking the measurement here for the volume of this liquid, using this graduated cylinder, you would read it as 1.4 milliliter. And this is how you would report it in your lab book. And it's 1.4 because you know that it's at least 1 milliliter because it's above that 1 milliliter mark, but it's less than 2. And so, but there's no little marks or minor marks between 1 and 2. And so the number 4 here is just the estimated digit. It's considered uncertain, right? It's not certain, and so it's more like your guesstimated digit. So you would report it again as 1.4 milliliter. But when you look at the second graduated cylinder here, you would report it as 1.50. So you may read it as 1.49, maybe 1.51, but the idea here is that you have 3 significant digits for this measurement, right? You know that it's at least 1.5 because you have these little marks here. Okay, so this is 1.5 minimum, at least. And then you have to have an estimated digit, the uncertain digit. And so because of this, because of the fact that it has 3 significant figures, this measurement is more accurate compared to the first graduated cylinder. So what about measuring the length or the distance and temperature of an object or a liquid? How do we take into account significant digits? It's actually the same concept as the previous one for volume, and it's pretty simple. So let's say we have 2 different rulers here, ruler A and B. Ruler A up top contains major marks 0, 1, 2, and 3, and ruler B at the bottom has minor marks, right? So you have 0, 1, 2, and 3, and then you also have 0.1, 0.2, 0.3, 0.9, so on and so forth. And so let's say that we're measuring this piece of rod, metal rod, and with the first ruler up top, ruler A, you would read this as maybe 2.3, right? Because you know it's at least 2 centimeters, but less than 3. And then the next digit is just going to be a guesstimated digit. And so you would report it as 2.3 centimeters. With the second ruler at the bottom, ruler B, you know that it's at least 2.3 centimeters. Okay, and then you would have an estimated digit for the second ruler, and it can be anywhere between 1 and 9, right? You could report it as 2.35, you can report it as 2.36, 2.34. It doesn't matter. As long as you have that estimated digit, it would be considered an acceptable measurement. And so, in any case, the 2.35 measurement is the more accurate measurement, which makes ruler B the more accurate tool in measuring the length of this rod. All right, and again, the idea is the same for temperature. So let's say that we have 2 different thermometers here. And again, thermometer B on the right has minor marks, whereas the thermometer on the left doesn't have any little marks. And so you can immediately conclude that the thermometer on the right is the more accurate thermometer. So how do we report the measurements properly? And again, this is important whenever you're performing experiments at the lab, how to read measurements properly. So with the first thermometer here on the left, you know that it's at least 99 degrees Celsius, but it's below 100 degrees Celsius. So you have to have one estimated digit. So you can report it as, let's say, 99.1 or 99.2, maybe 99.5. Any of those would be acceptable measurements. With the thermometer on the right, you know that it's at least 99.5 degrees Celsius. And so you have to have an estimated digit, which in this case could be 0, could be 1, 2, 3, so on and so forth. And so again, the thermometer on the right would be the more accurate measurement.